What's up, Raiders? We're going to take a look at a level 3 pulley system here. And while the inclined plane makes this free body diagram for the box on the ramp a little more complicated, the overall steps to analyze this pulley system are the same as for a level 1 and level 2 pulley system. So let's jump right in here. So the first thing we'll do is we'll take the block on the ramp and we're going to draw a free body diagram showing all the forces acting on it. We'll do the same thing for the other block. And then when we apply Newton's second law to them, F net equals ma, we're going to see that we have too many unknowns for each individual equation. So we're going to solve it as a system by getting the expressions for force of tension for each of them and then setting them equal to each other. Same exact steps we did for level 1 and level 2 pulley problem. So I'm going to identify the direction of motion, and that's going to be positive. And that's going to show up when we do our F net equals ma equations, so we can identify which terms will be positive, which will be negative. So for the 10 kilogram block, regardless of being on the ramp, gravity still wants to pull it straight down. So the force of its weight is straight down. Mass times gravity, 10 times 9.8. So the block on the ramp weighs 98 newtons. Now, because of the incline, a percentage of this weight is still going into the plane, but not 100% of it like it would be on a horizontal surface, and a percentage of the weight is going down the plane, and that's where we're going to figure out the trigonometry. So a percentage of the weight is going into the plane, so I'll call it FWIP, force of weight into the plane, and a percentage of the weight is going down the plane, FWDP. And now we can translate this vector right down here without changing its value or its angle. FWDP. And let's say the angle of incline is 30 degrees. Well, with the right triangle that we just created, this angle is going to match the angle of the ramp, so that's 30 degrees. So right now we can get the components of the weight. So these aren't second and third forces in addition to the weight, they're just the components of the weight. So relative to this 30-degree angle, the force of weight into the plane is adjacent to it, and we know the hypotenuse, so that combination of adjacent and hypotenuse sets us up for cosine. So cosine of 30 degrees equals the force of weight into the plane over the overall force of weight, which is the hypotenuse, so 98. Multiply both sides by 98. So the force of weight into the plane is going to be approximately 84.87 newtons. And that should make sense in general, because if it's a 30-degree incline, it's closer to horizontal than vertical, so the majority of the weight should still be going into the plane. Now we're going to figure out the component of the force of weight going down the plane, and relative to the 30-degree angle, this is the opposite side, and we know the hypotenuse, so that combination of opposite and hypotenuse sets up for sine. So sine of 30 degrees equals the force of weight down the plane, the opposite side to the angle, over the hypotenuse. So multiply both sides by 98. And the component of the force of weight that's going down the plane is 49 newtons. Notice it's significantly less than the component of the force of weight into the plane, which again should make sense because the ramp's a lot closer to horizontal at a 30-degree angle than it is to vertical. Now, continuing on with the free body diagram for that block on the ramp, in response to the fact that some of the weight is going into the ramp, the 84.87 newtons, in response to that, the ramp pushes back with that reactionary normal force. So notice this is part of what makes this more complex. With simpler scenarios where a block is on a horizontal surface, force of weight and the normal force, as long as there's no other vertical forces, are equal and opposite. Well, here, that's no longer the case. But if you look at this block, while it is moving along the line of the ramp, it's not moving this way at all, so it has to be in equilibrium this way. So the reactionary normal force of the ramp pushing back has to be equal and opposite to the component of the weight going into the plane. So we can identify that force is about 84.87 newtons. And this 10 kilogram block is being pulled up the ramp by the tension in the rope. So that's force of tension. And in response to the blocks moving up the ramp, friction always opposes motion. So ultimately, when we apply Newton's second law here, while we have multiple things labeled here, the only ones we have to worry about are the ones in the line of motion. So it's going to be the battle between the force of tension in the rope pulling the block up, and then the component of the weight going down the plane and the friction working against the motion are going to try and stop the block from moving up the ramp. So now let's calculate what that force of friction is. Force of friction is mu times the normal force. And we were given the coefficient of friction in this problem. If the coefficient of friction is 0.25, and the normal force, again, it's not equal and opposite to the weight, it's equal and opposite to the component of the weight going into the plane. So it's about 84.87 newtons. Or in other words, it's about 25% of that normal force. So it's about 21.22 newtons. So now that we've identified every force we can in our free body diagram for this block, other than the unknown force of tension, now let's apply Newton's second law to it. F net equals ma. And remember, force is a vector quantity, direction matters. So if we're analyzing motion along the line of the plane, the only forces that matter are the ones that are along the plane. So we got the force of tension up, the force of weight down the plane, and the force of friction. Those three forces are going to be responsible for this 10 kilogram mass accelerating up the ramp. Now I'm going to go back to what we did in the very beginning. We identified the direction of motion as positive. So that means when we analyze this block going up the ramp, any force going up will be positive. So that translates to the force of tension will be positive, but the force of weight down the plane and the force of friction are working against that motion, so they're going to be negative values. So the force of weight down the plane is 49 newtons, and the force of friction is approximately 21.22 newtons. So notice we're stuck at this point, like we've been in other pulley system problems, where in this one equation we have two unknowns. We don't know the force of tension pulling the block up the ramp, and we don't know its acceleration up the ramp. So all by itself, we can't analyze this equation. So now we're going to analyze the simpler hanging block, get an expression for force of tension there, and then we'll be able to set it equal to the other force of tension, because the tension in the rope's the same everywhere. So the free body diagram for this block is a lot simpler. I don't want to clog up that diagram too much. I'll just do it separately down here. So it's a 30 kilogram block. So you've got the force of tension holding it back because of the weight of the block on the ramp, and then gravity trying to pull it straight down. So you've got its weight pulling down, mass times gravity, 30 times 9.8. So it weighs 294 newtons. And again, the force of tension is unknown. We do know this force of tension holding back the hanging mass is the same as the force of tension pulling up this one. And that's how we're ultimately going to be able to solve this as a system of equations. So I'm going to put my little reminder for myself that in the beginning of the problem, we made the direction of motion positive, and this hanging block's moving down. So in a minute, when I apply Newton's second law, F net equals ma, down will be positive. All right, F net equals ma. And it's just these two forces. The force of tension plus the force of weight, those two forces are going to be responsible for this 30 kilogram mass accelerating. Now I'm going to take into account signs here. The force of tension is against the direction of motion, so that's going to be negative. And the force of weight is in the direction of motion, so that'll be positive. And notice we have the same problem that we did with our analyzing the other block. We have one equation, but we have two unknowns. We don't know the force of tension, and we don't know the acceleration. So I'm going to rearrange this equation to get an expression for force of tension, and then I'm going to do the same thing with my other equation, analyzing the block on the ramp, rearrange this equation to get an expression for force of tension, and then set those force of tension expressions equal to each other. So I'll add force of tension to both sides. Because this is negative force of tension, we want force of tension expression. So 294 equals 30A plus the force of tension. Subtract 30A from both sides. So the force of tension can be expressed as 294 minus 30A. So it doesn't solve it for me, but at least have an expression for it now. So now I'm going to rearrange this equation to get a force of tension expression. So the force of tension minus 70.22 with the combined effect of the component of the force of weight down the plane, the force of friction equals 10A. Add 70.22 to both sides. So the force of tension can be expressed as 10A plus 70.22. So again, because this is one rope connecting both the blocks, the tension of the rope is going to be the same everywhere. So this force of tension is going to be equivalent to this force of tension. So now we can solve this as a system with substitution. The force of tension on one side equals the force of tension on the other side of the pulley system. So now just substitute both our expressions in. 294 minus 30A equals 10A plus 70.22. It's approximately equal to that. So I'll add 30A to both sides. So 294 equals 40A plus 70.22. Subtract 70.22 from both sides. So 223.78 equals 40A. Divide both sides by 40. So the acceleration of this pulley system is approximately 5.59 meters per second squared. And just a quick reflection to make sure that this makes sense. No matter what, the block on the ramp holds back the hanging 30 kilogram block at least a little bit from free fall. So this acceleration, it should always be less than 9.8, and it should always be a positive number because we've made the direction of motion positive. So that's always a good, simple, quick check to do when you get your answer at the end, is the acceleration needs to always be less than free fall, but greater than 0. All right, Raiders, hope this helps.